Hello everyone, my name is Mohammad Hafizul Islam and I am a PhD student at University of Central Florida. Today I will present our work BranchSpec Information Leakage Attacks Exploiting Speculative Branch Instruction Executions. This work is done under the guidance of my advisor Dr. Fanny. Modern processors are highly optimized for performance with a proper understanding of the corresponding security implications. Recent out-of-order processors rely heavily on speculative execution to obtain high performance. In the last few years, vulnerabilities arising from speculative execution have changed the landscape of microarchitectural security significantly. Particularly during transient execution, while architectural states are guaranteed to be squashed, changes to microarchitectural state remain beyond speculation and can enable potential side channel exploits. These attacks are extremely dangerous as they allow unintended data to be exfiltrated via side channel. Prior works have demonstrated attacks in several components like caches, TLB, and functional unit. Among various transient execution attacks, branch predictor is one of the most critical components. While BPU is usually utilized to trigger speculation, the actual transmission of secretive data typically relies on hardware components such as caches. On the other hand, prior works have also shown that branch predictor unit can transmit data in non-speculative domain. If branch predictor unit can be used as a side channel to transmit data in a speculative domain, it will create a new attack vector where unintended cross-domain secrets could be leaked through branch predictor, which can enable an even more dangerous transient execution adversary. So, in this work, we want to answer the following question. Can we use branch predictor as a transmitting medium in transient execution domain? Before diving into details, first let me briefly talk about the basics of branch predictor design. Here, we are particularly interested in the direction prediction for conditional branches. Modern processors maintain a pattern history table or PST for direction prediction. Each entry in PST contains a finite state machine using a saturating counter. For example, here I am showing a 2-bit saturating counter which has 4 states. In a one-level predictor, the branch address is used to select one entry in PST. Modern processors also feature a 2-level BPU design where past branch history is combined with branch address to index PST. A selection logic is used to switch between one of these two states of prediction. It is widely known that cache state changes during a speculation are not restored by default even if a speculation is incorrect and squashed. Here we are interested in the following question. Do PST changes remain after a speculation? To answer this question, we design a micro benchmark with major code snippets shown on the right. Here branch 2 is nested under branch 1 and it's the branch to be targeted. On the left, I am highlighting the PST entry which is used by branch 2 in one-level prediction mode. In the first step, we initialize the target PST entry to a predetermined state. Let's assume branch 2 is executed with not taken outcome, which sets the PST entry to weakly not taken. In step 2, we trigger the transient execution of branch 2. To do so, we trigger speculation of branch 1 and make sure that branch 2 is executed speculatively and is resolved before branch 1. The PST entry of branch 2 is updated during a speculation. In this example, branch 2 is taken under a speculative path, so the PST state is updated to weakly taken. Later on, when branch 1 is resolved, the speculation is detected and all the subsequent instructions including branch 2 is squashed. In step 3, we execute the branch 2 again with taken outcome and check if branch 2's PST state changes during a speculation can indeed impact code execution later. If branch 2 is mispredicted and the code block of branch 2 will have longer execution time due to overhead of speculation, and otherwise it will have shorter execution time. Figure 1 shows the execution time of targeted code block in step 3 when the outcomes of branch 2 in a speculation are different. Here we observe that if the speculated branch 2 is taken, which is the same as the actual outcome of branch 3 in step 3, we observe consistently shorter execution time. On the contrary, if branch 2's outcome in step 2 is different, we see longer execution time. Based on this experiment, we reached to the quick observation that branches executed in the speculative path changes PST entry which is not restored even after speculation is corrected. We note that this can create a new attack variant of transient execution attack in which the BPU can be used as a transmission medium in a speculative execution. We have notified Intel about our findings prior to the publication of this work. Now that we established speculation changes BPU states, we demonstrate how an attacker can abuse this phenomenon to transmit speculatively accessed data in side channels. One example code gadget in victim is shown on the right. Here, although array 1 in victim branch BV may not contain any secretive information, it may be tainted with unintended data since it is executed speculatively, specifically in this case using out-of-bound memory load. In the first step of the attacker initializes the PST state of victim branch to a predetermined state. The attacker uses a branch BA which is congruent to BV to initialize the PST state. Specifically, here the attacker is executing BA twice with taken outcome. This converges the state of the PST entry to one of the taken states. Then the attacker triggers the victim execution so that the victim executes branch BV speculatively. In the speculative path, the victim branch accesses certain unintended data controlled by variable X, which later determines the outcome of victim branch. After victim branch is resolved, the corresponding PST entry will be updated and the changes remain after victim execution is completed. Now that we know the target PST entry in a state correlated to the unintended secret accessed in a speculation, for simplicity let us assume the state was initialized to a strongly taken by the attacker. If the victim branch is not taken, the target PST entry will be updated to weakly taken. If it is resolved as taken, it will remain in a strongly taken. Now, in the third step, the attacker tries to probe the targeted PST entry and infer the unintended secret in victim address space. In order to do that, the attacker executes congruent branch BA twice again, this time with outcome not taken, and it checks execution latency for the second inference. We can see that BA will be correctly predicted when victim branch's outcome is not taken, which leads to shorter execution time of BA's code block. In contrast, BA is mispredicted when victim branch is taken, that leads to longer execution time of BA. This way, attacker can successfully infer the value of victim branch's condition which is dependent on cross-boundary data. Let's look at the key results and characteristics of our BranchSpec attack. Firstly, this is the first attack that shows side channel in a speculative domain using BPU. We also discussed the possibility of leveraging our attack vector to target sensitive applications such as crypto algorithm, image processing, and machine learning programs. Even if the application doesn't contain any secret data dependent branch, BranchSpec can potentially target a benign nested conditional branch to speculatively access and leak secretive data. Secondly, we note that BranchSpec enables stronger capabilities for transient execution attacks. Specifically, this allows an attacker to use BPU for an end-to-end exploitation. More importantly, BranchSpec can utilize more common code patterns in the victim's code base. For example, in the upper right side, we show the example of Spectre v1 code gadget which recurs memory indirection that is not commonly available in real applications as shown in prior works. On the bottom right, we show several code blocks that can be leveraged by BranchSpec which has simpler memory access patterns. We also have shown a covert channel using BranchSpec that enables a Trojan to secretively transmit unintended data to the spy through modulation of branch execution. Here on the right side, we show the communication protocol of covert channel using BranchSpec where spy and Trojan runs on separate processes. On the bottom left, we show the actual latency traces observed by the spy corresponding to the Trojan's data transmission. Now that we know the information leakage threat in a speculative branch execution and the severity of this attack, how do we defend against this? Existing system-level defenses are ineffective against this type of attacks because it mostly targets attacks based on indirect branches. System-level defenses like Rathpoline, IBRS, and others don't have any impact on PST-based attacks like BranchSpec. On the other hand, there are several architectural-level mitigations that can be adopted. Most straightforward solution can be restoring PST state after transient branches execution has finished. But this requires additional hardware overhead for checkpointing and it may have restoring overhead in the critical path of program execution. Besides this, PST update can be delayed for speculative branch execution until at the commit time or at least when they can no longer be squashed. Another mitigation could be leveraging invisible update for speculative branch. More details about attack analysis and discussions of defense can be found on the paper. Nonetheless, this work highlights that secure branch predictor design has to be considered as first order of design priority. In conclusion, we discovered that branches executed in speculation changes PST state which are not restored after transient execution finishes. We highlight that this vulnerability allows BPU to be used as transmission medium in transient execution attacks. We demonstrate new forms of side and covert channels exploiting the discovered threat. We also discuss several potential mitigation techniques for future secure branch predictor design. Thank you for attending this talk. If you have any questions, please send them to this email.